Hey everyone! Today we're diving into a powerful tool called Bayes' Theorem. It's one of those things that once you get it, feels like a little bit of magic. It gives us a way to update our beliefs about the likelihood of an event as we get new evidence. The video is titled Bayes' Theorem, the Trick No One Told Me. Imagine you have some initial idea about how probable something is. Bayes' theorem is the rule that tells you how to revise that probability based on new information. It's a way to learn from data. It's a method for formalizing the process of updating our initial assumptions with observed facts. By the end of this video, you'll be able to, first, understand the core idea of conditional probability. Second, you'll be able to apply Bayes' theorem to real-world problems. And third, you'll be able to interpret what the results actually mean. So, grab your coffee and let's get started. By the end of this, you'll feel like you've unlocked a secret. Before we jump into the main event, we need to quickly review the foundation that Bayes' theorem is built upon. Conditional probability. It might sound fancy, but it's really just the probability of an event happening given that another event has already happened. In other words, how does the knowledge of one event change the probability of another? We write it like this. Of a vertical line B, you read this as the probability of A given B. The vertical line is our symbol for given, and the formula for it is the probability of both A and B happening, divided by the probability of the event we know has occurred, which is B. It's the probability of the intersection, divided by the probability of the condition. Let's work through a few examples to make this concrete. Let's kick things off with our first example. Suppose we're talking about a group of students. The probability that a random student plays a sport is 50%, and the probability that a random student is involved in a school club is 40%. The probability that a student does both is 30%. We can write this down. P of S, the probability of playing a sport, is 0.50. P of C, the probability of being in a club, is 0.4g. And P of S intersection C, the probability of both, is 0.30. Now for the question. If we know a student plays a sport, what's the probability they're also in a club? This is a conditional probability. We're looking for the probability of being in a club, C, given that they play a sport, S. So we write this as P of C given S. Using our formula, that's the probability of both, divided by the probability of the given condition. We plug in our values. 0.3 divided by 0.5, that gives us 0.60. This means that among the students who play sports, 60% are also in a club. Notice how that's higher than the 40% who are in a club in the general population. The knowledge that a student plays a sport increased the probability they're in a club. That's the core idea of conditional probability. Let's look at another example, this time involving a deck of cards. Suppose we draw a card at random from a standard 52 card deck and then place it back. The first event, A, is drawing a red card. There are 26 red cards, so the probability is 26 out of 52, which is 1/2. The second event, B, is drawing an ace. There are 4 aces, so the probability is 4 out of 52, or 1/13. Now let's ask a conditional question. What's the probability that we drew a red card, given that we drew an ace? Think about this intuitively. If you know you drew an ace, how many of the 4 aces are red? 2, right? The ace of hearts and the ace of diamonds. So the probability should be 2 out of 4, which is 1/2. Let's see if the formula agrees. First, we need the probability of both events. P of red and ace. How many cards are both red and an ace? Just 2. So P of red and ace is 2 out of 52. The formula tells us P of red given ace is P of red and ace divided by P of ace. That's 2 over 52 divided by 4 over 52, which is just 2 over 4. That simplifies to 1/2 or 0.5, just as we thought. This example shows that sometimes the conditional probability is the same as the original probability. That happens when the events are independent. If we had asked for P of red given king, it would also be 1/2. But knowing you have an ace changes things. It's a key part of how our minds work when we're given new information. For our third conditional probability example, let's use a table to organize some data. This is a great way to visualize these problems. Let's say a local high school has 200 students. We surveyed them about their favorite academic subject and whether they prefer morning or afternoon classes. Here's what we found. We have a table showing the number of students for each combination. For instance, 40 students like math and morning classes, and 30 students like history and morning classes. This table summarizes our sample space. Let's ask a question about this data. What's the probability that a student likes math, given that they prefer afternoon classes? We're looking for P of math, given afternoon. The beauty of the table is that it makes our sample space for the condition very clear. The condition is that the student prefers afternoon classes. So, we only care about the afternoon column. In that column, we have 20 students who like math, 50 for history, and 30 for science. The total number of students who prefer afternoon is the sum, which is 100. This is our new denominator for the probability calculation. Out of these 100 afternoon lovers, how many like math? The table shows 20, so the probability is 20 out of 100, which is 0.23. We can also use the formula. P of math and afternoon is 20 out of 200 total students, which is 0.17. P of afternoon is 100 out of 200 total, which is 0.50. Dividing them, 0.17 divided by 0.50, we get 0.2. The results are the same. This confirms that focusing on the conditional sample space is the right way to think about conditional probability. Okay, that's enough foundation. Let's build up to Bayes' theorem. It's essentially a special application of conditional probability. Remember our formula. P of a given B equals P of A and B over P of B. We can rearrange this formula algebraically by multiplying both sides by P of B. This gives us P of A and B equals P of A given B times P of B. This is a very useful formula in its own right. It tells you how to get the probability of both events from one of the conditional probabilities. We also know that P of A and B is the same as P of B and A. So we can write a mirror version of our first equation. Since the left sides of these two rearranged formulas are equal, their right sides must also be equal. This gives us the relationship that P of A given B times P of B is equal to P of B given A times P of A. And now we just need one more step. We divide both sides by P of B, and voila! We arrive at Bayes' theorem. It states that the probability of A given B is equal to the probability of B given A times the probability of A, all divided by the probability of B. This is the trick and the secret. It allows us to calculate P of A given B, which is often what we want to find, by using P of B given A, which is often what we can easily measure or look up. We use a special vocabulary to describe the terms in this theorem. P of A given B is the posterior probability. It's the probability after we've seen the evidence. B. P of A is the prior probability, our initial belief before any new information. P of B given A is the likelihood, the probability of seeing our evidence if our initial belief was true. And P of B is the marginal probability of the evidence. Okay, let's put this theorem to work. Our first example is a classic one, involving a medical test. Suppose we are testing for a rare disease. The prevalence, or the prior probability of someone having the disease, is just 1 in 1,000. So, P of D is 0.001. The test is pretty good. The probability of getting a positive result if you have the disease is 99%. And the probability of getting a positive result if you do not have the disease is 5%. Now for the burning question. You get tested and the result is positive. What's the probability that you actually have the disease? We're looking for P of D given positive. Most people, when they first see this, think the answer is around 95% or 99%. But let's use Bayes' theorem to see the real answer. It can be quite surprising. Here's our formula, but with D for disease and plus for positive result. We have everything except P of plus. We can find that using the law of total probability. The probability of a positive test is the probability of a true positive plus the probability of a false positive. Plugging in our numbers, we get 0.00099 for the true positives and 0.04995 for the false positives. Adding them up gives 0.05094. This is the probability that anyone who gets tested will get a positive result. Now we have all the pieces for Bayes' theorem. Let's put them together. The top is P of plus given D times P of D. The bottom is P of plus. The calculation gives us approximately 0.0194, or about 1.94%. This is much lower than the intuitive guess. Why? Because the disease is so rare. Even with a good test, the number of false positives, those who do not have the disease but test positive, is much larger than the number of true positives, those who do have the disease and test positive. It is a fantastic illustration of why prior probabilities are so important. Let's try a less somber example. This time, we're talking about weather. Imagine you live in a city where the sun shines 80% of the time. You have a special app that predicts sunny weather. It's accurate 90% of the time it actually is sunny, but it sometimes predicts sun even when it's cloudy, with a 15% false positive rate. Let's translate that. P of S, the prior probability of sun, is 0.80. P of plus given S, the likelihood of the app predicting sun when it's sunny, is 0.90. And P of plus given S prime, the false positive rate, is 0.1y. Here's the question. You open the app and it says tomorrow will be sunny. What's the actual probability that it will be? We're looking for P of S given plus. Let's set up our Bayes theorem. It's the probability of the app predicting sun if it is sunny, times the probability of sun, divided by the overall probability of the app predicting sun. Again, we need P of plus, using our trusted law of total probability. The probability of a positive prediction is the probability of a correct positive plus the probability of a false positive. Don't forget the complement. P of S prime, the probability of it being cloudy, is 1 minus P of S, which is 1 minus 0.80, or 0.2. So P of plus is 0.90 times 0.80 plus 0.15 times 0.20, which equals 0.72 plus 0.03, giving us 0.7. Now we can finish up with Bayes' theorem. P of S given plus is 0.90 times 0.80 divided by 0.75, which is 0.72 divided by 0.75. That comes out to 0.96 or 96ths. This makes sense. Your initial belief in sun was 80%. The app predicting sun bumped that belief up to 96%. In this case, since the prior was so high, the app's prediction, even with its flaws, made you almost certain. It shows how the prior probability can sometimes dominate the evidence. For our third and final example of Bayes' theorem, let's explore a scenario where the evidence is actually less likely if our initial belief was true. Imagine a factory that has two machines, Machine A and Machine B. Machine A produces 60% of the total items, while Machine B produces 40%. Machine A is older and has a defect rate of 2%, but Machine B is newer and has a defect rate of just 1%. So our priors are P of A is 0.6 yes and P of B is 0.40. The likelihoods are P of defect given A is 0.02 and P of defect given B is 0.01. Now for the question. A customer receives a defective item. What is the probability that it came from Machine B? We're looking for P of B given defect. Here's the twist. The evidence we observe, a defective item, is actually less likely to come from our event of interest, Machine B. P of defect given B is 0.01, which is smaller than P of defect given A, 0.02. What will Bayes' theorem say? The formula will give us P of B given D is equal to the probability of defect given B times the prior probability of B divided by the total probability of an item being defective. Let's find the denominator P of D first. The overall probability of a defect is the probability of a defect from A plus A defect from B. That's 0.012 plus 0.04, which gives us 0.216. So 1.6% of all items produced are defective. Now we can solve for P of B given D. Plugging in our values, we get 0.01 times 0.40 divided by 0.016. That's 0.0004 divided by 0.16. The result is 0.25, or 5%. Let's unpack that. Our prior belief was that the item came from B with 40% probability. After finding out it was defective, that probability dropped to 25%. Why? Because a defect is twice as likely to come from Machine A. So the evidence of a defect makes you more likely to believe it came from machine A and less likely to believe it came from machine B. This demonstrates how Bayes' theorem can shift your belief in either direction, depending on what the evidence implies. Let's summarize what we've learned and then tackle some practice problems. We started with the concept of conditional probability, which tells us how the probability of one event is affected by our knowledge of another. Then we derived Bayes' theorem, a formula for reversing that conditional probability. The key insight is that our initial belief, the prior probability, is just as important as the evidence itself. Bayes' theorem shows us how to balance those two things to get a more accurate picture of reality, the posterior probability. It's a process of using observed data to update our degree of belief in a hypothesis. Now it's your turn. I've prepared 3 practice questions with solutions to help solidify your understanding. I encourage you to pause the video, work them out on your own, and then compare your answers. You learn best by doing, so give it a shot. All right, here are your practice questions. Pause the video now to give them a try. Good luck. Question 1. Suppose the probability of snow on a winter day is 30%. A local weather app correctly predicts snow 95% of the time. However, it also has a false positive rate of 10%. It predicts snow when it doesn't snow. If the app predicts snow, what is the probability that it will actually snow? Question 2. A manufacturing plant has 2 assembly lines, line A and line B. Line A produces 70% of all items, and line B produces the remaining 30%. Items from line A have a 1.5% defect rate, while items from line B have a 2.5% defect rate. If a randomly selected item is defective, what is the probability it came from line A? Question 3. A bag contains 8 red marbles and 2 blue marbles. You draw 2 marbles from the bag without replacement. What is the probability that the second marble you draw is red, given that the first marble you drew was red? Okay, let's go over the solutions. How did you do? Solution for question 1. We need to find P of S given plus. We use Bayes' theorem. We calculated P of plus using the law of total probability. Plugging in the numbers gives us a final probability of about 74.3%. So if the app says it will snow, your belief that it will snow increases from 30% to almost 75%. Solution for question 2. Here we're looking for the probability that a defective item came from line A. We use Bayes' theorem for P of A given D. We found P of D using the law of total probability. The result is about 82.4%. This is higher than line A's 70% production share. This is because a defect is more likely from the line with the higher production, even though line B has a slightly higher individual defect rate. The prior probability of it being from line A is very strong. Solution for question 3. This one is a conditional probability problem. We are given that the first marble drawn was red. This changes our sample space. Before the first draw, there were 8 red marbles. After drawing 1 red marble without replacement, there are now only 7 red marbles left, and a total of 9 marbles. So the probability of drawing another red marble is simply 7 out of 9. So we've come to the end of our dive into Bayes' theorem. You've seen how a seemingly simple formula can unlock powerful insights by connecting 2 different conditional probabilities. The core idea is this: we don't start from scratch when we get new information. We start with a prior belief and use Bayes' theorem to formally and rigorously update that belief to a posterior probability. This process of learning from evidence is at the heart of so many fields. It's used in machine learning for things like spam filtering, in medical diagnosis, in legal analysis, and in the scientific method itself. It's not just a mathematical formula, it's a way of thinking rationally about uncertainty. You've now been let in on the trick no one told you about, a way to quantify how new information should change your mind. I hope you enjoyed this guide. Keep practicing these types of problems, and soon this theorem will feel like second nature. Thanks for watching.